All 40 of us. Okay, so yeah, well, let's try to have a little bit of fun, I guess, whatever that looks like with Laplace transforms. Friday before spring break. Um, yeah. Cool. So, announcements on the day, right? We got worksheet 9 coming in tonight. We're going to talk about step functions today, and then spring break. Big ups to people traveling in process right now. That's pretty hardcore. What are we going to talk about? Well, we're going to work a little bit more initial value problem. And then we're going to start talking about these step functions, which starts getting into why we started any of this discussion at all. And that is we want to develop new and different functions that we're going to represent the following. Let me just get out the prop for the day. Here's my mass spring system, let's say, mass spring system. And here's my experiment. Boom, start the clock. All right, nothing's happening, right? And now I'm going to come at this thing. I'm going to hit it. And now something's happening, right? So the life of this mass spring system is do nothing, do nothing, do nothing. And then all of a sudden energy gets pulsed into it. And then it's going to sound. And that sounding for us is represented by sinusoids. Okay? So that change in behavior, that switch in behavior is totally the nature of step functions. Audio is varying. Does it sound like I'm in a tin can? You get quiet then loud? Okay, if anybody tries out the stream, no, it's just quiet. Well, I mean, that just might be me getting quiet and loud. I've raised the levels a little bit. I can raise them a bit more if it's too quiet for your max audio output. Okay, cool. There we go. That's good. No one in... Yeah, 2 o'clock. They didn't even say that. It was like a ghost town. We tried hard, and that's really the point. Trying. So, first, let me bop us over to Canvas and talk about some stuff that I've put out there. Right, so if we go into the Zoom links for Canvas, what we'll see is that there's a set of videos uploaded to YouTube, and I tried to break them out so that they were pretty small, and then I labeled them too so that we have an idea of what's going on. And so these are videos from, it's actually strange, some of it's from fall of last year, but then during fall of last year, I showed while I was teaching videos from summer, the semester prior, and so these are going to be some quick go-to spots about the step function if you're in need of quick action there, but we'll talk about some of that today. But I wanted to let you know that it's out there. And then we're going to go over to the pad. We're on lecture number 28. We're going to talk about initial value problems and the step function definition. So what we're going to do is we're going to talk generically about the initial value problems. Oh, yahoo! We're ahead at 2 p.m. Good job, 4 p.m. That's some gusto right there. So we're going to talk about the initial value problem generically. So if I were to sum up at this point, I would tell you that Laplace transforms trade derivatives for multiplications. Right? They undo the derivative, but you pick up S multiplication as the side effect, and that's fine. Integral transforms will generally do that to derivatives. And then how should we think about it? We're trading calculus for algebra, and maybe that doesn't seem like the best trade, but you got to remember when this stuff was developed, they were willing to trade calculus for algebra all day, because algebra at least had rules. It might not be fun, but there were rules. Not like NOM. Inhomogeneous, we're studying a second order linear constant coefficient inhomogeneous initial value problem. In our last opening slide, right, we derived how we got here, but I want to break this down for a second. We want to notice that the initial conditions for the initial value of problem appear in this numerator right here. And so something else that appears in this numerator is this piece of the puzzle. And what is that piece of the puzzle? This piece of the puzzle in the denominator is the characteristic equation for the ODE, right? So that characteristic equation has roots, and those roots were totally the roots we were finding for second order stuff. And that would break into 3 classifications. Classification 1, real, different, roots. If you're talking about real different roots, what sort of mathematical function are you talking about? You're talking about e to the at, and so you're talking about table entry number 12. Okay. Then we could have real repeated roots. And if you're talking about real repeated roots, you're talking about e to the at and te to the at. And so now you're talking about 12 from before, but you're also talking about table entry number 16. And then the third thing that can happen is you could get complex roots. And so if you're talking about complex roots, you're talking about e to the at cosine bt, and then e to the at sine bt. So why am I mentioning this? Well, knowing ahead of time the functions that the IVP should be creating or promoting, supporting, spawning, however you want to think about it, that will guide where you look at the table. You don't want to just haphazardly go through the table. You want to go in with an objective in mind. And so for complex roots, where am I looking? I'm looking at table entries number 18 and 17. Right? That would be these right here with exponentials and sines and cosines, but the exponent in the exponential could be 0, so we could also just get straight sinusoids, so you're talking about 13 and 14 as well. Okay? So, if I were to color this in pink, where are case 3? Case 3 is 13, case 14, case 17, case 18. I'm already knowing, based on the initial value problem, where I'm going to go digging into the table. That's the idea. Then, for the real repeated roots, where are we going to head to the table? Well, real repeated roots, that's going to get me table entry 12 and table entry 16. And then, for real different roots, where am I going to head to the table? I'm going to head to table entry 12. So just from the structure of the initial value problem, I already know that I'm going into these table locations. What else can I know? I can know that for real different roots or repeated roots, the algebraic tool here is partial fraction decomposition. And then, for complex roots, what might we have to use? We might have to complete the square. All right, so I'd mentioned algebra at the 2 p.m. class, and I said something, and somebody said in chat, you're making this bold assumption that we're good at algebra, and I totally understand. Algebra and intensive algebra was something that was probably longer ago in your mathematics training because you've been getting a lot of training in calculus since then. So how would I mitigate the algebra? How would I deal with it? I would get an idea of where we want to go into the table and the algebraic tools that are going to come up so that that's guiding us. Because the downside of algebra is sometimes you could be doing algebra, but it's just not helping, right? So this is my little crib sheet about what I should be doing and when I should be doing it, right? And so one last thing I would say about this term right here is since it comes from the initial conditions and since it has the characteristic equation in the denominator, this has y homogeneous terms in it. So when I figure out this chunk of the Laplace transform machinery, this chunk is telling me about homogeneous terms in my solution. So that's guiding me. Well, if that's the case, what about this second term? Well, this second term has f of s, which comes from little f of t, right? So little f becomes capital F, and this has to do with the particular terms, okay? The particular terms are going to be coming from capital F of s because they are from the inhomogeneity, but the inhomogeneity on the Laplace side gets mixed up with this characteristic equation as well. And so they're also, so it has yp and homogeneous terms in it as well. Right here, the capital F has the particular terms. The characteristic equation is carrying homogeneous information, and you got to break those up. And how are you going to break them up? You're going to break them up with partial fractions. Okay? So that's the algebra landscape associated with an initial value problem. If step 1 is something you're comfortable with, you will get to things that look like y of s. The initial condition terms are going to give you homogeneous-like stuff that'll guide how you use the table. The particular term, the inhomogeneous term, will give you particular solutions that you would have gotten through muck, but here you've got to try to break them up. Anytime you're trying to break functions apart, you're using partial fractions. Okay? And then the last thing I'll say before we dig into some problems is that when you get to this stage right here with your initial value problems, there's an inclination to join the fractions together. But looking at what I have written here, if you join the fractions together, you're kind of mixing up particular stuff with homogeneous stuff when you don't need to be. And so for that reason, when you join these two fractions together, if you do that, the problem generally gets much harder. You got to keep them separate. The whole goal on the Laplace side is break everything into separate pieces and then consult the table. Okay. So that's what I have to say about that. Okay, I'm going to fade out. I'm going to freeze. I'm going to notice that I said, oh, tell them about the videos on Canvas. I have told you about them, so that is fantastic. And then when I unfreeze, I'm going to put the 2-minute timer up. We're going to practice getting to... Okay, actually, yeah, no. Yeah. Okay, I'm coming back. Unfreezing. I'm going to put the 2-minute timer up, and let's practice with this differential equation. This is going to have a repeated root in it, so that's something that we haven't seen yet. So I'll put 2 minutes on the clock. All right, that's it on the clock. So I think you want to be jumping probably into this stage right here and foregoing all the cursive and curly notations if you're now feeling comfortable with this idea of transforming the whole ODE. And then you can even put the initial conditions in and not quote the whole transformation, right? You can just slide in for y of 0. Well, that's -1. So every time I see a y of 0, I'll put in -1. And then there's a y prime of 0, and I know that that is 5. So I'm going to put a 5 in there. I transformed the left-hand side of the equation, and then I'm obligated to transform the right-hand side of the equation. So what I get now is capital Y of S When I group the terms, I see the characteristic equation come back again. And then I get negative 1 times negative s is positive s. And then I get a negative 5 for my purple term. And then I get a negative 1 times a negative 1, but watch out, there's a 4 out in front of all that, so I get a positive 4. And then on the right-hand side, I have 6 over s plus 2. So now all I have to do is solve for capital Y of s. Solving for capital Y of s means two things. I scoot over all these initial conditions, and then after I scoot those over, I divide through by this characteristic equation. Right? And let's recognize that s squared plus 4s plus 4, this can be factored into an s plus 2 quantity squared. Okay? So when I solve for capital Y of s, I'm going to have a negative s, and then what? Negative 5 plus 4 is going to be negative 1. Move it over to the right. It's going to be positive 1. And then I have a plus 6 over a pre-existing s plus 2. So I've scooted my initial conditions over. I'm keeping the initial conditions separated from the term that came from the inhomogeneity, and then I divide through by the characteristic equation, which is s plus 2 quantity squared. And then there was already an s plus 2 in the 6 over s plus 2 term, and so I pick up 2 more, so that's a cubed right there. So there it is. That's my solution in Laplace side. Okay? So, what would I tell you about this solution? Step 2 is going to be about getting all of this stuff table ready. When I'm thinking about getting it table ready, what am I thinking about doing? I remember that the Laplace transform will act on the individual terms a piece at a time. And so, I'm going to notice that for my capital Y of s, there are really 2 terms that I have to deal with. And I'll call this first term y1 of s to organize my work. And then I'll call this term y2 of s. And so what I'm going to do is actually I'm going to start molding together step 2 and step 3, because really, if we get comfortable with step 1, which is the transformation of the equation, and step 3 is just use the table to get back, that can kind of be merged into step 2, which is really where the heavy lifting's going on. Okay? So before I get on with step 2, right, let's think this through a little bit. When I'm thinking this through, let me use, I don't know, I'll use this red color right here. What would I be thinking with this equation? I'm going to put a little star here so that I can sneak down here and do a little star thought processing. Well, what would the characteristic equation be? It'd be r plus 2 quantity squared is equal to 0. So that means my r is negative 2. But I already know the homogeneous solution should look like c1 e to the negative 2t plus c2. Because the root is repeated, the second term picks up a t, and then I get an e to the negative 2t. Right? So that's my my homogeneous solution. I can see that coming. And so what is that telling me? That's telling me I need table entry 12 for the exponential, and then I need a table entry that gives me t times that exponential, right? And so we were talking about that, and we'll look that up in a second. But let's see a little more into the future, and that is that I can also spot my particular solution, right? My particular solution is going to be based on this 6e to the negative 2t. So I would think, oh, you're going to want an undetermined coefficient amount of e to the negative 2t. But then I check back with the homogeneous, and they're the same function, so I got to throw t on here. But then I check back again, they're the same function again, so I got to throw 2 t's on here. So my particular solution would be t squared. And remember the fun that was, I had to take 2 derivatives, cram it all into the differential equation. A bunch of product ruling happens. And I deal, and I pick up my capital A. Okay? All of that information is sitting here in Laplace side. Let's take a look. First thing. Now that I've broken it up into y1 and y2, I'm going to do y2 of s. I'm going to color code it in green first. So we see that connection, but I'm going to get back to blue here. And that is 6 over s plus 2 quantity cubed. Where did this function come from? Let me highlight that. This function, which has the 6 on it in Laplace side, here's that 6, came from this term right here. And what should this, or where did this come from in the ODE? It came from the right-hand side, the term that didn't have any y's or y primes or y double primes on it. So what should y2 correspond to? y2 should be related to this particular solution that we would have gotten from Mach. But the particular solution that we got from Mach was t squared e to the negative 2t. So I use that to inform where I go in my table. And where should I go in my table? I should go to table entry 16. Because what does table entry 16 have? It has powers of t multiplying e to the at. Okay? So I check out table entry 16. I scoot over to the Laplace side. I say from table entry 16, can I figure out my a? My a is equal to negative 2. And then my n is equal to 2. So I can spot that from table entry number 16. And then what I'm going to do is I'm going to write the 6 out front, and then I'm going to need, what do I have in the denominator? I have an s minus minus 2. You don't have to write it that way, but I'm just being explicit there. And then that's raised to the 2 plus 1 power. Okay? To highlight the a and the n. And so, what does this formula tell me? This formula tells me that if my n is equal to 2, I need to have a 2 factorial in the numerator. I don't have a 2 factorial in the numerator. I totally could from that 6, right? Like the 6 could be crafted to look like a 2 factorial. But suppose that was some prime number and I couldn't get any good factors out of it. Well, forget it. I'm just going to put a 2 factorial in the numerator. But then I'm going to need to put that 2 factorial in the denominator. And so, what does this imply? This implies that the inverse Laplace transform of y1, or sorry, y2 I'm working on, going in reverse order because this was the easier one, is going to be 6 divided by 2 factorial times the inverse Laplace transform of 2 factorial over s plus 2 quantity cubed. And then what is that equal to? That's equal to, well, 2 factorial is 2, 6 is 3 times 2, so this is 3 times t squared e to the negative 2t. And what does that correspond to? That corresponds to the particular solution. It could have more in there. I might need partial fractions to break it up. But in this case, because of this repeated root fiasco we got ourselves into, it doesn't need it. Okay. Questions about that? Okay, the real problem here is y1. y1 of s is equal to negative s plus minus 1. I'm going to factor the negative off, so the numerator has just a s minus 1 times a negative over an s plus 2 quantity cubed. No, not cubed. Squared. There we go. All right. If the homogeneous solution has an e to the negative 2t and a te to the negative 2t in it, then what am I thinking about? I'm thinking about table entry 12. And what does table entry 12 tell me? It tells me that e to the at transforms to 1 over s minus a. Right? So this is table entry number 12 right here. Just to throw it up there. I'll move this 16 down here. Okay. And so what should I be trying to spot? I should be trying to spot 1 over s plus 2's, and then some s plus 2 raised to a power. I need to see mixes and matches of 17 or 12 and 16. So this is the partial fraction trickery that we need. Ready? If I see a linear term raised to a power in the denominator, then I write that as a over that linear term plus b over that linear term raised to the power of 2. If I had a cubed there, I would have a over s plus 2 plus b over s plus 2 squared plus c over s plus 2 cubed to catch all the higher order terms. It's just a rule for partial fractions. Now, I'm going to set this partial fraction up, but I'm not going to do it. I felt that that's really where the 2 p.m. class went from like kind of okay to like, no, just I'm done. Totally done. Right? So I'm going to set it up to show you the key point that you want to remember from partial fractions, and then I'm going to really trick my way out of it. And it only works in this case, but the trick's pretty fun, so we'll have a good time with that. And then I'll hyperlink out in the 2 p.m. section on our page where you can find the partial fraction madness. But this is what I want you to remember about the partial fraction decomposition that you saw in calculus. To join the fractions, I'm going to get a times s plus 2 squared plus b times the denominator of a and then divided by the multiplication of the two denominators. Okay, this is where the most common mistake is. What is that mistake? Right where the cursor's pointing, that's the denominator on the right. Where the laser pointer's pointing, that's the denominator on the left. They are not the same denominators. If they are not the same denominators, I cannot make the numerators equivalent. Right? So if you, from this step right here, make the numerators equivalent, there's going to be an error. The reason why is that this denominator has picked up an extra s plus 2 in it. But what will always happen here is that one of these s plus 2's in the denominator will cancel with one of these s plus 2's in the numerator. And then you can go standard partial fraction decomposition work afterwards. And then once you do that partial fraction decomposition work, you'll figure out your a, right? But what is this function really in disguise? It's an exponential, part of your homogeneous. And then you'll know your b, but what is this function in disguise in the Laplace side? This is your t times e to the negative 2t. So that's what you're finding here, is you're finding out your two homogeneous solutions. Okay. And partial fractions will do it. And when you're thinking about real roots, you're thinking about partial fractions. But I'm going to trick my way out of this repeated root problem. And here's how it goes. I'm going to scoot down a little bit. And then in this void area between the two slide regions, I'm going to show you the trickery. Or okay, you have negative s minus 1 over s plus 2 quantity squared, right? Here's the trick. I'm going to add 2 to the numerator. I just can't add 2 to the numerator, so I got to subtract 2 from that numerator as well. But what is this equal to? Leave a negative clear out in front of everything so we don't confuse ourselves with that. Take the s, take the plus 2, divide it by s plus 2 quantity squared. Right? And so I'm going to highlight those in orange. Take the s, take the plus 2, keep the denominator. And then what's left behind is a negative 1 times a negative, or minus a negative 2. And so what I'm going to have is negative 3 over s plus 2 quantity squared. What's s plus 2 divided by s plus 2 quantity squared? Be 1 over s plus 2, right? And then I have minus 3 over s plus 2 quantity squared. And there we go. This only works for repeated roots, but you can totally bypass the partial fraction decomposition if you're cool with that. You just got to get real crafty with the adding of the number 0. If you're not with that, then that's fine. Go ahead and do the partial fraction decomposition. But what does this all mean at the end of the day? All of this means that the inverse transform of capital Y2, or Y1, I guess, is equal to negative 1 over s plus 2 transform. So that's going to be a negative e to the negative 2t. And then a negative times a negative, 3 over s plus 2 squared. So that's going to be plus 3t e to the negative 2t. And so what terms are we talking about here? We're talking about homogeneous-like terms. And then at the end of the day, the inverse Laplace transform of capital Y is equal to the inverse Laplace transform of Y1 plus the inverse Laplace transform of Y2. Yeah, that second method is slick. Less procedural, but slick. And then what do I get? I get negative e to the negative 2t plus 3t e to the negative 2t plus 3t squared e to the negative 2t. Okay. All right. And there's another initial value problem. And Lucas is down. All right. So what you want to see here is that these things are procedural. If I try to talk my way through it, it makes the problem pretty long. But if you just scrap out the algebra and bludgeon your way through it, knowing the procedures that need to be there, I mean, it's not the funnest thing that's ever happened in this world, but it's definitely not going to take you like 25 minutes to grind it out with a little practice. I mean, you're normally not telling somebody all the algebraic moves you're doing. You just do them. So I'm going to fade out, freeze, prep the next section. And I think I'm going to skip over this Laplace transform that I have here. And I'm actually going to clean up this next bit of mathematical stuff because I think probably this late in the game on a Friday right before spring break, we probably just want to see where this is headed. See what the next thing is that we're going to need to study. Okay. So here we go. We're going to switch over in 3, 2, 1. Okay. So I make a little note right here saying see posted video. I'm going to talk my way through this because we should talk through the original or the initial starting point of the new stuff. But you can go ahead and check out a video online there too. That's, I'll probably say roughly the same stuff, but maybe not. But here's the idea. All right. What we want to have now is something that's going to act like a mathematical switch because I can do things to a system. I can just have the system doing its thing. Maybe it's oscillating, maybe it's not. And then I can come in from the outside and do stuff to it. And when I do stuff suddenly from the outside world to the system's going to have a big change in behavior all of a sudden. And right now, we don't really have anything that deals well with changes in behavior. How should I think about changes in behavior? In mathematics, I think about functions that have changes in behavior as piecewise functions. Okay. And so what we're going to define here is called the unit or Heaviside step function. And it is the primitive set up for a piecewise function. So here's its definition. Yeah, it's named after a person, and you say heavy, but it's Oliver Heaviside, and so there's not an EA in there. Not that I spell it correctly every time, but this time I did. That's good. So, the function is u. U is going to have the argument t minus a. I could also write this as u subscript a of t. So u is the function. U means unit. Just like SIN means sine, right? This unit step function is taking in the argument t minus a, and what is it? It's the simplest piecewise function that I could write. And this piecewise function is 0 for all t values that are less than a. And then it is the number 1 for all t values that are greater than or equal to a. So what is this a in the argument and function statement all about? Here's an a, here's an a, here's an a, here's an a. A variety of different notations. What does it mean? Let's think about it graphically. This is what it means graphically. Here's the output time axis. And on the output time axis, there is this special point in time called A. So there's another A. And here's the idea. If t is less than A, the function is the number 0. So for all t values that are less than A, the function is 0. It's nothing. Nothing's going on over here. And then I have an open circle to represent that at t is equal to a, the function changes behavior, and the function changes behavior to the number 1. So here's the number 1, and at that point in time, the function becomes the number 1. And that's my switch. I think about this green region is the step function is being off, and by off, I mean 0. And then this purple region right here is the step function is being on, or the number 1. Right? And then when does that switch happen? That's told to me directly in the definition of the function when I write down the u function. It is at a seconds there will be a jump in behavior, a switch, a change between off and on. All right. So, how can we use this? Well, what we can use this function for is to write down in a non-piecewise way, because this is really a stand-in for a piecewise function, we can write down a piecewise function using the u's instead of this piecewise notation. That could be my f function. This f function is saying start off at t equals 0 and then have f be 0. But then f will grow linearly from 0 up until a seconds, and at a seconds the f function turns off and it does nothing. Graphically, what this looks like is well, there's green. Actually, let me bring in this point A. So at a seconds, this function changes. And what does it do? At 0 seconds, it's going to go up like y equals x, up until the point where it hits a units high. Okay, and then something else I should mention over here. Note, in Laplace transforms, it is assumed that t is greater than or equal to 0. Okay? So whenever I'm thinking about these things, what I'm really thinking is that everything left to the vertical axis, I'm not even going to worry about that. Why is that? Well, the Laplace transform integrates from 0 to infinity. It assumes that the user has set up their clocks so they start their clocks at time 0. Okay? You could shift stuff around and change that if you wanted, but that's just the classic definition. And then when t is greater than or equal to a, what does the function become? The function linearly increases, and then at time a, it becomes 0. So what could this mean? Think about a mass spring system. Here's my mass. Maybe it's oscillating around, or it's going to oscillate around. Maybe it's undamped. And then at time 0, what do? I stick an armature to it, and then I start pressing down. So there's a force that's going in the downward direction, and as time increases, I increase that force up until a seconds, where then I just back off the mass spring system entirely, and then I apply no external force and just let it do its thing. Okay? This is especially useful in circuits where you might have a variety of different things attached to the circuit that you can switch on and off in time, right? And maybe those external agents have different characters. And you can slam together lots of different characters, but this is a good entry point. So now what I want to do is I want to write f of t down. Here is its graphical representation. Here is its piecewise notation. And what I want to do now is I want to write down its step function notation. So here's the idea. When I start off at time 0, what's the function going to do? And b, it's going to be this green function increasing like y equals t. Right? So I'm just going to be t. Right? That's pretty good. But here's the rub. It's not always going to be t. Right? At some point, it's going to be 0. So you're like, oh, I've got it. You've got a t here. You want it to be 0. I'll help you out. I'll just subtract away t. That'll turn that t off. Except now what I'm talking about here is the 0 function for all time. Before, I was talking about the t function for all time. Now I'm talking about the 0 function for all time. And so what the step function is going to do is it's going to get in there and it's going to moderate. How is it going to moderate? It's going to moderate in the following way. You start off as t, and then I'm going to subtract away t, but I don't want to do that until a seconds. If you don't want to do something until a seconds, the step function is your friend. So you write down u, and then you say t minus a. So why would you do that? Well, what is this step function? The step function is equal to 0 for all t values that are less than a. Right? So when t is between 0 and a, say like right here, what's the step function going to be? The step function right here is going to be like, yo, I'm the number 0 right now. I'm not doing anything. And that t multiplies a 0. So all of this stuff is player 2, and player 2 is not in the game yet. Now time advances, and then all of a sudden a seconds happens, and now boom, player 2 jumps in the game and becomes the number 1 for all t greater than or equal to a. And so now player 2 comes in, it becomes the number 1. 1 times t is t, times a negative is negative t. And so from that point on, this second term cancels out the first term, giving me 0 for the rest of time. And you could keep going. You could have multiple different domains where things switch on and off, and you add them on, and then you use a subtract or a step function and a subtraction to take them off at a future time. So what are some morals from this? We want to take some notes. Step functions imply time delays. That's how we should think about them. I want to have the power to turn things on and off and wait and stuff like that in time. And then we use subtractions with step functions to turn features off. Okay. So the big question that remains then is, now that I have a way to very concisely express behavior changing external forces to my mechanical and electrical oscillators, the real question is, how does this act under Laplace transform? Okay. And so I'll write here answer, see posted videos to get a head start. But we will do this after break. Okay. I don't really have enough time right now to start that sort of Laplace transform work, and I'm sure I've borrowed many couple minutes from after classes from the lot several times over the semester, so this is roughly where the last class ended. We should probably end here too. And so I will end for the day, and I will say have a good spring break. If you are interested in getting started on this stuff, those videos can help you out, but we'll come back and we'll talk about that stuff after spring break, and then we'll finally talk about the hammer hit. But other than that, if you're still listening, plane flighter, have a good plane flight. And for the rest of you that are not at DIA or wherever airport that might be, have a good spring break and take care.
Thank you.
Recording stopped.